For decades, the global aerospace hierarchy followed a predictable path. China's military aviation sector operated effectively as a client state, relying on Russian engineering, platforms, and export licenses to modernize its air force. That dynamic has fractured. The current operational reality is defined by domestically produced hardware, like the J-20 stealth fighter. Meanwhile, the Russian Su-57 program, originally positioned as the apex of Eastern stealth design, remains virtually stagnant, struggling to field combat-ready squadrons. The scale of this divergence is massive. Current estimates show the operational J-20 fleet is approximately 10 times larger than the entire active Su-57 inventory. Beijing has functionally abandoned the Russian design path, forging an independent aerospace trajectory that now outpaces its former mentor. The question is how a former client state rapidly scaled a highly complex fifth-generation fighter program while the originators of that technology stalled. Building a stealth aircraft is notoriously hostile to mass production. The required precision geometry and radar-absorbent materials traditionally force a slow, bespoke assembly process. China bypassed these limits by tearing down the firewall between its defense sector and its broader economy, integrating military procurement directly into its massive civilian manufacturing ecosystems. This system is currently projected to output more than 100 stealth aircraft every single year. Volume on that scale creates a new strategic reality, shifting the geographic threat boundaries and operational geometry of the entire Pacific. To understand why China succeeded, we have to look at why Russia failed. The traditional Russian aerospace model relies almost exclusively on isolated, state-owned heavy industries. That closed loop is highly vulnerable. International sanctions choke off the flow of critical components. What gets through often hits a second bottleneck: persistent engine shortages, leaving near-completed airframes stalling entirely. A modern low-observable jet engine requires intricate engineering that cannot be easily mass-produced under duress or without specialized tooling. Even without these external pressures, the old Soviet-style industrial base suffers from rigid, built-in scalability limits. It was never designed for rapid expansion. The result of these compounded bottlenecks is that the Su-57 operates as a boutique, experimental configuration rather than a theater-dominating fleet. Contrast that fragility with the Chinese manufacturing ecosystem. Through civil-military integration, Beijing sources critical components from a vast network of commercial tech sectors. Decentralizing the supply chain bypasses the bottlenecks that crippled Russia, allowing production to scale rapidly past 100 aircraft per year. Operational formations of J-20s serve as physical evidence that this high-volume production model is actively populating frontline squadrons. The primary threat is no longer an individual airframe. The weapon is the resilient, hyper-scaled industrial base that can constantly replace and upgrade those airframes. Scaling the production of a single land-based airframe is only the first phase of this strategy. The production engine is now diversifying into the J-35, a platform engineered specifically as a navalized variant for the carrier fleet. Embedding the J-35 into carrier strike groups allows the Chinese Navy to project a capable fleet air defense network into the open ocean. But stealth airframes are delivery vehicles. The physical danger to adversary networks lies in the advanced weapons they carry. Long-range effectors like the PL-15 and PL-17 air-to-air missiles are designed with the range and speed required to threaten Western aerial dominance. Pairing the oceanic mobility of a J-35 with the deep strike reach of a PL-15 creates a mobile, lethal threat umbrella that can be positioned anywhere in the theater. Integrating stealth volume with long-range firepower enables a specific operational doctrine, the suppression of enemy air defenses, or SEAD. In a coordinated SEAD mission, stealth aircraft systematically hunt down and blind opposing radar networks before traditional aircraft even enter the airspace. This capability poses an immediate problem for regional powers like Japan and Australia. Faced with a high-volume stealth fleet, these nations find that existing stockpiles of standoff missiles and passive defensive measures are inadequate. To counter the numbers, allied nations are forced into a massive financial commitment, investing in sophisticated airborne early warning platforms and integrated air defense networks. By leveraging manufacturing scale, Beijing is executing a financial war of attrition. Adversaries must expend staggering resources simply to maintain baseline situational awareness. Looking at the geopolitical geometry of the Indo-Pacific, the impact of this production becomes clear. The region is defined by two critical geographic boundaries, the first and second island chains. The volume of land-based J-20s, backed by J-35 carrier groups, creates an area denial perimeter that engulfs the first island chain. When you factor in the extended kill chains of the PL-15 and PL-17 missiles, that danger zone stretches even further east, pushing well beyond the second island chain. The objective is clear. Beijing is using industrial mass to physically challenge Western air dominance deep into the Pacific Ocean. Looking back at the historical baseline, the former client state has outpaced its original supplier. The J-20 and J-35 programs elevate China to possess the world's second-largest fifth-generation fighter ecosystem. Russia's inability to integrate its civilian tech sector has sidelined it in aerospace competition. Ultimately, in a modern peer-to-peer conflict, advanced stealth technology is useless without the resilient, high-volume manufacturing base required to deploy it at scale.